The first question asked how vasoconstriction, causing precapillary sphincters to close, would affect heat loss from radiation, conduction, and convection. So vasoconstriction in precapillary sphincters closes off these sphincters so that less blood flows through. So less blood enters those capillaries, less blood is exposed to the conditions, less water is leaving, and there's less hot water near the surface. That's the big one. Capillaries near the surface of the skin constrict, and so there's less radiation because the surface of the skin is cooler, and radiation is directly proportional to the temperature of the surface. So with the hotter blood kept more interiorly, you get less radiation. You get less exposure of that warm surface to skin, to the wind, and so you get less losses from convection, and you get less exposure of this warm surface of the body to cold surfaces, so you get less loss through conduction. So why is it wise to ice a bruise, a sprain, or a muscle tear, but not a cut or a puncture? Well, the inflammatory reaction is a response to potential pathogens. So icing a bruise will reduce the inflammatory response, but icing a cut reduces an inflammatory response, but that allows potential pathogens to invade. The inflammatory response helps to do a rapid mix of macrophages and activated white blood cells into an area to attack any potential invaders. So the inflammatory response is wasted on a bruise. The problem is a body can't tell, the skin can't tell whether all that tissue damage from a bruise might have broken the skin, and so it does the inflammatory response anyway. But we can ice it and reduce both the swelling, and we also even can shorten the healing time. The neural circuits for a rabbit that would pass a freshly eaten bolus of food from the small intestine to the cecum for fermentation. This was a messy, every homework I graded had a messy structure here, so I'm going to do a quick one. Here is the anus, colon, cecum, and I'll walk you through this one over here in a moment. But what we'd want is some molecule that's present only from fermentation in the cecum, so that a bolus of food that has that molecule in it gets detected. So here's some of that molecule coming out, and here is a sensory neuron that has a receptor to that molecule. So here's our sensory neuron, and that sensory neuron we'll take it to an inner neuron so that we have some choices. But that inner neuron then will send to, let's just make it a motor neuron here, because what I'm going to do is have that motor neuron synapse on a sphincter muscle, circular muscle that wraps around, so that when this bolus of food comes down, this sphincter muscle is contracted. So our sphincter muscle contracts, they get shorter and wider, and that closes off the cecum, so that the only way our bolus of food can go is down to the anus. On the other hand, what we'd want is, if we have a sensory neuron that another one here that's detecting that compound, and if that compound is active, if that compound is absent, then we want to relax the muscle to the cecum, and so here's a sphincter muscle to the colon, and this neuron is has sodium channels that cause APs unless it is inhibited. So this neuron would normally be closing the sphincter to the cecum, but if this molecule is there, so if this molecule from the fermentation is there, that means this is something we want to pass out, and so if it's present, we inhibit this motor neuron. It does not constrict here, and the bolus of food leaves. But if there's nothing there, we lose the inhibition. This relaxes. Then if there's nothing here, we lose the inhibition, and then this neuron keeps having sodium coming in, and so this muscle contracts, and the bolus of food goes in here. I'm going to walk you through this again. I'm sorry, this was a complex circuit. So if we have food with, I'm going to make this food green. This is food that does not have anything from the fermentation. So that means it is not going to activate this sensory neuron. It is not going to inhibit here. And this is going to constrict. And so that food is going to go in here and be fermented. Once it is in there, it picks up these fermentation molecules. And so when it goes back out and is re-ingested, here it is now with these fermentation molecules. Now it activates this circuit that constricts these muscles, so it can't go to the cecum, which is good because it's already been there. And it binds here, and so now we activate this neuron. It inhibits this one that normally is constricting. And so these muscles relax. So those relax, and our food goes out. So this is essentially what this one shows. It detects a fermentation chemical, that's the red one, that activates a sphincter muscle that closes the cecum. And here's fresh food. There's chemical signal in the fresh food. If the fresh food is detected, it activates a sphincter muscle that closes the colon. Simpler than my circuit. And this one would work. Bacterial ruler problems continue to be hard, so I'm just going to walk you through my answers. I got a mix of mostly correct answers and some that were pretty far off. So the clue here is that even though typical cell is about 10 or more likely 20 microns, but this is in the lung, and we already know this is just part of a red blood cell. So clearly these are really thin, which is what you would expect in a lung, a really short path length. And the thinnest cells you have are capillary endothelium, these here, and lung epithelium, these here, because of the selection for short path lengths. And you have a clue. There is a plasma membrane. I pointed it out in the question. Here is a plasma membrane, this thin black line. That thin black line is plasma membrane along here. So if that's 7 to 8 nanometers or maybe 10 nanometers, then this distance here, so from here to here, is probably at least 10 of these thin black lines, and maybe a bit more. This one is a little less than 10, and this one looks like it's a little more than 10, maybe as many as 20. And so you've got something like 30 or 40 plasma membrane widths. So 30 or 40 times 7 or 8 nanometers, that gets you in the neighborhood of 300 to 400 nanometers. So it's a pretty short path length from here to here. And the second question was, is this distance consistent with an animal that can do sustained heavy aerobic exercise? And yes, it is. This is approximately the same as for a human. These varanid lizards, where this image was taken from, they are fast predators. And they are unusual among reptiles in their high metabolic rates. What's the width of the complete image? It's about 5 or 6 times this, and that's what people gave. In this case, it's about 2 microns. And most people had an answer here consistent with their answer here, which was good. At the point of an arrow, is this the correct location for basement membrane? It is. We would expect basement membrane if we have air out here, epithelial tissue, here's our epithelial cell, and we'd expect basement membrane underneath it. Similarly, a capillary has epithelial tissue, very thin, and we'd expect basement membrane underneath it going this way. So this is exactly the right location to have basement membrane that's being produced probably both by the lung epithelium and by the capillary endothelial cell, which is endothelium of a capillary is an epithelial tissue. Next was, could this object just below the P, this thing, be a blood platelet? And is it the right size? It is about the right size. It is about the right shape. And yes, it should be surrounded by a membrane, and it looks like it might be. Now, I can't find, reptiles in general don't seem to have platelets. I can't find for a varanid lizard. They do have higher blood pressures than most other reptiles. And so they might have a use for them, but I can't find any evidence that they do. So based on that, maybe not. But I didn't expect you to know that reptiles don't have platelets. The next question was, a person expresses half the normal of chloride channels, and what effect would that have on the digestive system in the mouth, so that'd be saliva, in the stomach, and the large intestine? So here we are in the mouth. Here's the lumen of a salivary gland down in here. And there's an NKCC transporter moving in the chlorides. They just haven't shown the sodium and the potassium here. And here's chloride moving in, but we have half the number of chloride channels. So this chloride channel is missing. And remember, the sodium is going through. This is a tight junction that is specifically able to allow sodium through, but not others. So we have less chloride coming in, which is going to mean we're not going to have as much salt in the saliva. And really importantly, to make your saliva, you move the sodium and chloride in, and then you need aquaporins to allow water to follow. That's how you get the liquid part of your saliva. So less water following the sodium and chloride, therefore a drier mouth. In the stomach, we need a proton pump, and so here is this proton pump. In this case, it's a proton potassium exchanger. Potassium keeps cycling around, but the chloride means to move across to balance the charge. And so if we have less charge in here, then we're going to have more of a difficulty getting the protons in. The protons have to bind here in order to move across. And that means we have to keep moving enough chloride in here to allow to maintain the charge balance. Otherwise, the protons that are already there are going to repel the protons that try to get near this transporter. So less acid to digest and make pepsin from pepsinogen. What about in the large intestine? Well, we're going to have fewer chloride channels here, which would make it harder to recover sodium and sodium here and chloride because we've got fewer channels, and we're going to reduce this transporter as well. So we're not going to maintain the same chloride gradient, and we're not going to be able to recover sodium and chloride as well. And then secondarily, again here, also, especially if you're not using a transporter like this is also an area where moving ions out, the chlorides and the sodiums, means we move water out. And so you're going to have watery feces. Diarrhea would be a problem. Number 5, a mouse overexpresses collagen in all of its blood vessels, expressing collagen where there should be elastin. Now there's a number of ways to answer this question, and I'll just show you one. So the rate at which blood is pushed out of the ventricle, well, with collagen it's stiffer, it's harder to move. So we may have a stiffer heart itself. The valves may be harder to open. You may need higher pressure to open them. And of course, to expand the arteries coming out of the heart, to pump blood out of the heart, you have to stretch the arteries to push the blood into it a bit. And so that's also going to be. So what's going to happen? This person argued you're going to need higher pressure needed, so a stronger heartbeat, and that will make the blood move out faster. And there'd also be less unless you really increased the heart rate, and you could match it. It could be about the same with a stronger heart rate and a faster heart rate. They argued less blood flow through the capillaries for the same kinds of reasons, and that makes sense. Again, could be compensated for by higher pressures and a stronger heartbeat. The optional question was a mutant. Their helper T cells are secreting their cytokine at all times, so they don't need to be stimulated. How will that affect the response to a virus? And it's going to be faster. The response wouldn't need to wait for that second confirmation from the cytokines. In other words, they don't need the helper T to also bind, and so the response would be faster. That would be nice, a faster response to an invasion. However, the mutation would make an autoimmune disease much more likely, much easier, because we don't need that secondary confirmation signal, and that means a rogue killer T cell that just happens to bind to a self cell wouldn't need a helper T cell that is also a rogue. And so we're more likely to get a autoimmune disease.